How do we find solutions to a linear system of equations? Here I've given you 3 examples of linear systems. Each example has 2 linear equations and 2 unknowns. Let's look at the first one in blue. Let's solve this linear system. Now before we begin, let's recall what it means to solve a linear system. That means we need to figure out what values for x sub 1 and x sub 2 satisfy these 2 linear equations. And what we can get is 3 different options. The first option is just one solution, so we get an x sub 1 equal to a number and x sub 2 equal to a number. The second option is we get infinitely many solutions, so there's infinitely many numbers that satisfy this x sub 1, x sub 2. And the third option is we get no solution, so we can't find an x sub 1 and x sub 2 that satisfy this system. So let's solve the system. This one's actually not that bad to solve. All we have to do is just add these 2 lines together. We'll get 4x sub 1 is equal to 16 because this cancels, and we get x sub 1 is equal to 4. And then to solve for x sub 2, I can take either one of these lines. I'm going to take the bottom one and solve for x sub 2, so I get x sub 1 minus 6 is equal to x sub 2. So then just plug in 4, we get x sub 2 is equal to negative 2. Oops. So this is our solution. Okay, and we can also double check the top one if we want to. We'll get 12 minus 2 is 10, so that works. Well, look at this one compared to this last system. This last system is exactly what we need. It gives us the solutions. Okay, let's solve the second one. Now the second system is less complicated than the first one. All we have to do, because it tells us exactly what x sub 2 is, we just plug it in right here and we get x sub 1 minus 4 times negative 2 is 12. X sub 1 plus 8 is 12, so x sub 1 is 4. We get the same solution. We get x sub 1 is 4 and x sub 2 is negative 2. Okay, so something we can notice about all of these is that for all of them we get the same solution, but all of these are different linear systems. They're different because they have different equations written out. However, they have the same set of solutions. So these 3 linear systems are equivalent. And what I mean by equivalent is they have the same set of solutions. Now they're not equal because for them to be equal they would have to have everything you see here would have to be here and here as well. So they're not equal, but they're equivalent. So this one's really nice. We're given the solution very quickly. This one is not too bad. We've solved one of the variables and we just have to plug it in to find the other one. And this one takes the most work. So what we're going to do is we're going to have a more complicated system. And what we're going to do with that system is we're going to try to either get it into this form where we solve for one of the variables, or in this form here, which this is the nicest form to get it into. It's really quick. We can find the solution. So what we're going to do is we're going to take a linear system and we are going to find a less complicated equivalent system. So let me write that down. So what we want to do is we want to replace a complicated system with an equivalent system that's easier to solve. To do that, we're going to have to talk about 3 types of elementary row operations. So there are 3 operations we can use to obtain an equivalent system. These are called elementary row operations. You're going to use these a lot. So I would definitely write these down, but you'll get used to each one of them. So some things we can do. The first one is we can change the order of the equations. Notice in the first example, if I switch these two, if instead of writing 3x1 plus x2 is 10, I put this one here and then I put this one here, I'd get the same set of solutions. I've just reordered the linear system. So that doesn't change the set of solutions. Something else we can do is we can multiply both sides of an equation with a non-zero number. When you multiply an equation by a non-zero number, you're not changing the set of solutions. The last thing we can do that's going to help us find an equivalent system is we can add a multiple of one row to another row. And this will not change the set of solutions for that system. Let's look at an example. So here I have a linear system of 3 equations and 3 unknowns. What I want to do, you can see that this is a more complicated linear system than the problem we did a little while ago. My goal right now is to get this looking something like this. So I want to solve for x sub 3 and then have a second equation, the one right above it, to be solved. Well, we have a coefficient of 1 in front of the x sub 2 and then any number here. These stars mean they can be any number in front of this x sub 3, and this can be any number. And then I want a coefficient of a 1 here, and then anything in front of x sub 2 and x sub 3 and anything here. If we can rewrite this system into this equivalent system, this will be a lot easier to solve, because here we have x sub 3, and to find x sub 2 we just plug that into here, and we can solve for x sub 2 just by moving everything on this side. And then once we have x sub 2 and x sub 3, we just plug those numbers into here and we can solve for x sub 1. That'll be a really quick way to find our solution. Here we've got something really complicated and it's hard to see the solution easily. Okay, so that's what we want to do. We want to replace this complicated system with something like this that's a little bit nicer. What I'm going to do is I'm going to use the matrix form we talked about in the last video. I'm going to make my matrix A, my matrix X, and my matrix B, where A is the matrix of just the coefficients. So I'm going to have 2, 4, 6, 1, 3, 5, and then 3, 5, 5, yeah. and then we have x1, x2, x3, and that is equal to 1, 1, negative 3. Just scroll up a little bit so you can see it. 1, 1, negative 3. The next thing I'm going to do is I'm actually going to create something called an augmented matrix, which is a matrix that has this matrix inside, a line, and then this matrix here. So what I'm doing is I'm getting rid of this x1, x2, and x3, because when I do these elementary row operations, we're not going to switch x1 and x2 and x3. They're just going to be left alone, so we don't have to really worry about that. You'll see in just a second. So let's create the augmented matrix. 2, 1, 3, 4, 3, 5, 6, 5, 5, and then 1, 1, negative 3. Now, my goal, let's look back just for a second. I'm going to scroll up. I want to replace that augmented matrix with, notice that I have a coefficient of 1 here, nothing here, nothing here, a 1 here, nothing here, and a 1 here. I want to get a matrix that looks something like this. Oops, let me undo that. And what I'm going to do is I'm going to use those elementary row operations. So if I multiply, let's say I multiply this one by a scalar, then I'm just going to multiply everything in this row by a scalar, because that's exactly what would happen to this linear equation. And then if I add a row, like if I add this row to this row, then what I'm going to do is I'm going to add, in my augmented matrix, I'm going to add the first row to the second row. So let me just show you what we need to do, and from there maybe you can catch on. Okay, I want to get a 1 here, a 1 here, a 1 here, a 0, 0, and a 0. Okay, so let's start by, let's zero out these two here. So what I'm going to do is I'm going to multiply this row by a negative 2. So I'm going to take row 1, I'm going to multiply it by a negative 2, and I'm going to add it to row 2. Let's do that. So I'm going to leave row 1 alone, and I'm leaving the last row alone. But I'm going to write this right on top, multiply this by a negative 2, so I get negative 4, this one by negative 2, this one by negative 2, and this one by negative 2, and then add it. So I get 0, 1, and then negative 1, and negative 1, right? 5 minus 6, and 1 minus 2. Okay. Now let's get rid of this 6. So what we're going to do is we're going to take negative 3 times row 1 and add it to row 3. So we're going to leave this alone. Alright, and on above this row I'm going to multiply every single thing. I'm using an elementary row operation. I'm going to multiply every single thing by a negative 3. So negative 6, negative 3, negative 9, negative 3. And then I add each one of these to this last row. I get 0, 2, negative 4, negative 2. Oh, sorry, I made a mistake. This happens. I'm sorry about that. You see, I saw 1, 1, and I just wrote that here. This is actually a negative 3 because of this. Sorry about that. So the only thing that changes here, write this a little bit better. So this is a negative 4, 1, negative 1, and this becomes a negative 6. Okay. So I've zeroed these out. Now let's get rid of this guy here. So we can multiply the second row by a -2 and add it to this one. Okay, I'm going to just put it down here. So I'm going to take -2 times row 2, and I'm going to add it to row 3. Move this down a little bit. So what do we get? 2, 1, 3, 1, 0, 1, -1, -1, 0. Okay, I'm going to write this. Now you can write it up here. I'm actually just going to put it right here. Actually on this one. 0, -2, 2, 2, multiplying every single thing by -2. Then add it. We get 0, -2, -4. And then my last step is I'm going to make this coefficient a 1. So I'm going to divide everything by 2 in the first row. So I'm going to take 1/2 row 1. And I'm also going to divide everything in the last row by a -1/2, just so I can make that a coefficient of 1. So if I do that, I get 1, 1/2, 3/2. One-half, 0, 1, -1, -1, and 0, 0, 1, 2. So let's take this and realize that this is the same thing as 1, 1/2, 3/2, 0, 1, -1, 0, 0, 1 times x1, x2, x3. This is equal to 1/2, -1, 2. And then from there, we can see that this is actually the system x1 plus 1/2 x2 plus 3/2 x3 is equal to 1/2. x2 minus x3 is -1, and x3 is equal to 2. Now we have that system we were talking about, this equivalent system where we have ones here and everything looks nice and it's an easier system to work with. First thing we can notice is that we already know what x3 is. x3 is 2. Now we can find x2 just by plugging this in here. We get that x2 minus 2 is -1, so x2 is equal to 1. And then for the last one, we just plug all that stuff into into this first line here. So we have x1 plus 1/2 times 1 plus 3/2 times 2. That's equal to 1/2. Get x1 plus 3 plus 1/2 is 1/2. So we get x1 is equal to -3. So this is our solution. x1 is -3. We can write it like this, where this is x1, this is x2, and this is x3. Or you could just write it how I've circled it. And you'll see that this solution that solves this, this one right here, this linear system, well, since this linear system is equivalent to our original linear system, which is way up here, I'm going to move a little bit. Keep moving. This linear system, they're equivalent. So our solution, which was -3, 1, 2, this is a solution to this system. And you can check it. You can plug in all of the numbers here, and you can see that you get a true statement for each one of these lines. So this is our system. We got one solution.